Welcome back, Hampshire chemistry students. Today in this video we're going to be talking about enthalpy, and our goal is that we can use enthalpy to calculate the energy released or absorbed during a chemical reaction. So in order to first discuss this, why don't we take a look at a chemical reaction. Specifically, we're going to take a look at the synthesizing of magnesium oxide, which is actually kind of cool. It's a common supplement. A lot of times people's magnesium levels in their blood need to be adjusted, so they might get some of this chemical. And it also can be used to help settle your upset stomach. That had nothing to do with the problem. I just thought it was fun. But so let's take a look at an actual setup of how we might see this problem in a chemistry homework or test, where we have some amount of magnesium oxide can be synthesized by heating magnesium metal in the presence of oxygen gas. Doing so releases negative 1,204 kilojoules per mole. Write the balanced equation for this reaction. So if you want to take a second and pause and try to write out the balanced equation for this reaction. So give it a shot. Okay. So the balanced equation should look something pretty simple like this. You've got two magnesiums plus one O2 goes to make 2 MgO. Now, what is important to note here is that we have not just in this reaction, not just chemicals, but also heat released. Remember that this idea of delta H, this is our enthalpy. This is the movement of energy, the movement of heat throughout the reaction. It's listed here as a negative because this is the energy that was released. It was an exothermic reaction. So here's the thing though. I do not have to have these two things separate. I can write them as a single reaction. And I actually have two choices for how I would like to write these. I can either include the enthalpy as part of the reactants here, or I can choose to include as part of the products. Why don't you take a few seconds here and see if you can figure out which one it might be. Okay, so when I look over here, I see that this is the energy that is being used to make the products. Whereas over here, this is energy that is being made. So what I see here is something that is being used up, that is being absorbed to make my product. This is when I see energy on the reactants, that means that I'm talking about something being absorbed. Also known as a endothermic reaction. Whereas over here, I see that it is part of the products. So if the energy is on the products, this means that it is energy that is being created, it is produced, it is released. Meaning that I am now dealing with an exothermic reaction. So, based on what our problem tells us that our heat was released, I would say that this form of the reaction where it is exothermic is going to make the most sense. And this nice balanced equation with our energy built into it is going to be very, very useful because it basically allows us to do some conversions. We've used conversions before where we set up a balanced equation, and that tells us, like this part, that 2 moles of Mg equals 1 mole of O2 equals 2 moles of MgO, but now it also equals negative 1,204 kilojoules. Remember that because this is on the product side, that's telling me that it's exothermic, so this value is going to be negative whenever I want to plug it into a calculation. Whew. So we've balanced our equation. We've included our amount of energy here in our exothermic reaction. Let's take a look at how we might apply this to an example problem. So I'm going to squeeze up here. This is the part that I'm focused on right now with my handy conversion factors. And let's take a look at a problem where I'm given 2.4 grams of Mg, and it's reacting completely, and then we're asked to figure out how many kilojoules of energy. So we're turning these grams into energy. Now you might notice that we don't have any equivalencies for moles, and we don't have any equivalencies for grams and energy. But what we can do here is we can do a three-step process. I can turn my grams of magnesium into moles of magnesium, and then turn those moles into kilojoules. So why don't you take a minute here and see if you can set that up, following our same pattern of our step-by-step conversions. So your first step is going to be pretty straightforward, just like any gram to mole conversion. You're going to divide by the molar mass in grams and multiply very simply by 1 mole on the top. So then we can now take our setup here and cancel out our moles of Mg and turn them into kilojoules. Now you might notice here that in this setup, this is the molar mass of 1 mole. But this amount of energy, the -1204, is equal to 2 moles of magnesium. So I want to make sure to include the coefficient 2 on the bottom for my magnesium. Now let's get our final answer here that we can just plug and chug into a calculator. And then I'm going to take my 2.4 divided by 24.31 times -1204 divided by 2. So my final energy ends up being about 59.4, rounded to 2 sig figs. So let's keep that at just very simply 59 kilojoules of energy. Make sure that that is going to include that negative sign that we found because we multiplied by -1204. That negative value tells me my actual exothermic answer. So that's about it for this video. And why don't you take a look at some of your homework problems and see if you can set up a similar equation for your reactions. Thank you guys for watching, and have a great day.